Today, we get to have a tremendous amount of fun with a really cool concept going on here. You need to tune in very carefully because for possibly all of you, this will be something brand new and kind of fun, I think. It's neat. This is section 7.4, obviously. And by the way, sometimes I say that there's going to be a quiz and then I forget to put the quiz questions in the material. I plan on having 4 quiz questions and I only think to do 2, one at the beginning, one at the end. I'm just not doing very well about the quizzes, but I would like to insert 2 or maybe 4 quiz questions as we go. I'll try to remember to do that. So remember, please, I'm still coming across a couple of you who are forgetting to designate A or B. When I sort these things, it's really easy for me to sort them and throw them into the right folders if you tell me what section you're in. And then identify it as being the quiz for section 7.4. So please follow this format in your subject line. And do not take a picture of your quiz answers, but put the quiz answers into the body of the email. There was a little confusion I found somebody who was confused about thinking that none of the assignments should be in the form of picture attachments. No, just the quizzes. Quizzes, put them in the body of the email. Regular assignments where you have to do page whatever, numbers whatever, I want to see a picture attached to your email. Now, and check your pictures for quality before you send them to me. Thank you. Moving on. Here we go. A little question I have here, mainly to myself. I'm finding that we have some guests, some non-Covenant Life School students and parents or just total strangers who have been tuning in to some of these videos. Welcome. I'm honored, and thank you for your support, whatever that may mean. But there's something here that occurred to me as I was writing this problem on the board that I wanted to mention to the whole world. I even found this statement, I think it was in this book, I'm pretty sure it's someplace in this book, where the author said that parentheses can mean multiplication. I violently object. If you think that parentheses mean multiply, that thinking can get you in deep trouble, and I've seen it get folks in deep trouble on test after test over the years. That thinking is wrong. Parentheses do not mean multiply. Example, 3 plus 5 plus 4. Do these parentheses mean multiply? No, they do not. There is no multiplication going on here. This is purely addition. It's 3 plus 9, which is 12. There is no multiplication here. Parentheses do not mean multiplication. So then why is this multiplication? Because what's in between this guy and the parenthesis? Nothing. It's the fact that there is nothing between them. That's what makes it multiplication. If I've got something real simple like 3 and 4, what makes this multiplication? Is it the parentheses? No, it's not the parentheses. It's the fact that there's nothing between them. That nothingness, that blank spot is what makes this multiplication. What if that were a plus? It's not multiplication anymore. Parentheses do not mean multiplication. It's the fact that there's nothing between them. That's what makes this multiplication. The invisible multiplication dot right there. All right, a little side note there. Let's move on. So this is example 1 from page 305. As you can see, this is the beginning of section 7.4. And what do? Well, distributive property. Our old friend from way back. You've been doing distributive property for decades. No, you haven't. For years, perhaps. Yes, you have. We multiply this guy by both of these. Why? Because it's addition. This is the distributive property of multiplication over addition. Why do we call it the distributive property? Because I'm distributing. I may have mentioned that in an earlier video. It's called distributive because just like when I give a test in a class, I pass out the papers. I distribute the papers to everybody, or I could go to Walmart and distribute the coronavirus to everybody if I have it, distributing it, passing it out to everybody. Everybody inside gets one. That's why it's called the distributive property. Don't mess it up. So, we have cubed root of y times cubed root of y squared. Just multiply, we get cubed root of y cubed. Plus, and then we do cubed root of y times another cubed root of y, gives me cubed root of y squared. Now let me grab something here. This was a gift from Casey some time ago, because I frequently mentioned knee-jerk reactions. Cool, huh? That's the real thing. Yeah, I don't know how Casey got hold of it. But anyway, a real knee thingy bobber. Doctor hits you on the knee and your knee goes, pa-ching! Okay, I call that a knee-jerk reaction. Well, everybody calls that's what's meant by knee-jerk reaction. It's involuntary. He hits you and ping, your knee jerks without you even thinking about it. Here, a knee-jerk reaction, like, oh, that's just going to be y. No, it's not. That's a knee-jerk reaction. Do not say that. We don't know the cubed root of y squared. But we do know the cubed root of y cubed. The cubed root of y cubed is y. The cubed root of y squared is, well, there's nothing we can do. It's just cubed root of y squared. Oops, y squared, I said. Y squared. That's all there is to it. We're done. You cannot combine these. It's over. C'est fini. Even Einstein couldn't do anything more with that. We're done. All right, that was the first example. Second example is a little more interesting. Here's where it starts to get fun. Mr. Beer? Yes? We don't care much for your definition of fun. Well, I can't write and think at the same time. Sorry. 4 square root of 3 plus a lonely 1 square root of 2. We're going to multiply that dude by square root of 3 minus 5 square root of 2. You know, this is kind of reminiscent of binomials being multiplied. Guess what we're going to use? Yes, we get to review our old friend we haven't talked about in quite some time. We get to review FOIL. Firsts, outers, inners, lasts. Shall we review the cheer and how that goes? In front of my face here, I have a binomial, or I have two radicals being added together. I'm going to call it a binomial for now. It's not really a binomial. I have a binomial. I have another binomial. The firsts are this guy and this guy. The lasts are this guy and this guy. So what do we have? We multiply the firsts, we multiply the outers, we multiply the inners, and we multiply the lasts. So we have firsts, outers, inners, lasts. Yay, algebra! It's like a cheer. Firsts, outers, inners, lasts. Yay, algebra! Okay, so we're going to apply FOIL to this guy. We're going to multiply the firsts. That means this guy times this guy, reviewing the FOIL concept in detail for anyone who somehow in the past chapters never quite caught on to it. Here we go once again, what's meant by FOIL. So we multiply 4 square root of 3 times 1 square root of 3. Well, what's square root of 3 times square root of 3? We should all know that by now. Square root of 3 times square root of 3 becomes just plain 3. Because is it not square root of 3 squared? Is it not square root of 9? Is it not just plain 3? Yes. So we have here 4 times 3. 4 times 3 being 12. What about the outers now? Outers being these guys, the ones on the outside. That's going to be, watch out, negative 20 times, what's square root of 3 times square root of 2? Put them together. Square root of 6. Yes. So we have negative 20 square root of 6 minus 20 square root of 6. Then I for inners. Inners meaning this guy times this guy. That's going to be square root of 2 times square root of 3 is just square root of 6. So it's a positive plus square root of 6. And then L for lasts. The lasts being this guy, the last one here, and the last one here. That gives us negative 5 square root of 2 times, what's square root of 2 times square root of 2? You better say 2. 2! That's right. Square root of 2 times square root of 2 is 2. 2 times negative 5 gives me a minus 10. And we have reviewed FOIL. Are we done? Of course we're not done, because we can combine like terms now. I've got a 12 minus 10. And I've got negative 20 of these guys plus 1 of those guys. What's negative 20 of those guys plus 1 of those guys? Yep, minus 19 of those guys. We're done. That's a pain in the neck. You may think it is, but that's all right. We'll get over it. The third example in the book is a very special example. Square root of 5 plus square root of 7 times square root of 5 minus square root of 7. Hey, remember, let's put that one on hold for just a moment. There. Do you recall how to do A plus B? I know you do. I mean, it hasn't been that long since we studied these in glorious detail and did a zillion of them. You know what A plus B times A minus B is? It's simply A squared minus B squared. Why is that? You don't remember? No. This happens because if we did use FOIL, or if we used any other method we wanted to multiply these guys, something special happens with the middle terms. The firsts would give you A squared. The lasts would give you B squared. But what about the OI, I call it, the outers and the inners? What happens with them? The outers will be a minus AB. The inners will be a positive AB. Guess what happens to them? Oh, they cancel! Yes, they cancel. There is no middle term. So we have that old pattern that A plus B times A minus B is always going to be A squared minus B squared. Every single time. How glorious. All right, now, back to the original problem. This is a case of A plus B times A minus B. So the answer is simply going to be A squared minus B squared. Well, what's square root of 5 squared? You better know. I heard that. 5. And what's square root of 7 squared? Yeah, 7. So we have simply 5 minus 7. Remember, it's not plus, it's minus, because it's going to be A squared minus B squared. So we got a result of negative 2. Cool. There's something very special about this that we will address in a few minutes. Not quite yet, because I'm going in the order in which the book presents this. For right now, they just want you to observe and think about it. All right, we move on. Let's see. We now tackle something. For those of you who have had me for geometry, I know that you have seen this before, and you might have seen it in Algebra 1 as well. This topic is called rationalizing the denominator. To make the denominator rational, if it's not already rational. A quick review here. So things come to mind, especially since I know that we have the potential for outside visitors. Let me just review a couple quick concepts here. Try to go through this quickly. Why do we call rational numbers rational? Rational numbers are rational because they are rational numbers. Rational numbers are numbers that can be written as a ratio. Therefore, they are rational numbers. But we don't pronounce it rational. I kind of wish we did pronounce it rational, but we call it rational. And the symbol for the rational numbers? Remember, a ratio looks like a fraction, yeah, a ratio. And if you take 3 and divide by 4, the answer to that is called the quotient. The quotient. That's why we use Q as the symbol to represent the rational numbers, because ratios are quotients, and quotient starts with Q. All right, another little detail here, denominator. How in the world do you remember the difference between the numerator and the denominator? Well, I've heard many suggestions such as N for north and D for down. Well, that works. But wouldn't it be nice if it actually made sense? Well, what does it mean to numerate something? To numerate means to count it, to give it a number. To numerate, to numerate the number of desks in this room, I would count the desks. To numerate is to give it a number, to answer the question, how many? That's what it means to numerate something. What is a denominator? It's related to the word denomination. A denomination is a kind of something, like a kind of faith, such as Baptists and Presbyterians. A denomination, what kind? Or in money, are we talking about $1 bills or $5 bills or $10 bills? What denomination? To denominate, nom referring to a name, to denominate is to give it a name. So the denominator gives it a name and tells us what kind we're talking about. The numerator tells us how many. It numerates it. So 3/4, for example, 4 is the denominator. It denominates it. It tells us what kind we have. These are fourths. The numerator tells me how many. It numerates it. How many fourths are we talking about? We're talking about 3 of them. So 3 is the number of them. 4 is the kind of them. That's why they're called numerator, because it numerates. And why it's called denominator, because it's what kind it is. Okay, just thought I'd throw that in for fun. For those who've never heard that before, all of my students have heard that before. Okay, so rationalizing the denominator. Let's make the denominator rational. Let's start with this example. How about cubed root of 7/9? This comes from example 4 on page 306. Problem is, we can split this if we want to. We can split it into cubed root of 7 over cubed root of 9. Now, it's not a bad idea to split it on your paper before doing this next step, but it's not required that you split it. You can do the splitting part kind of in the head. But here's the concept. Folks, I'm sorry, we don't like, or we don't know, and we also probably don't like, the cubed root of 9. It is not 3, because 3 cubed is not 9. Oh, woe's us. But here's the deal. There's nothing wrong with these expressions, with these numbers. They just happen to be in bad form. We don't leave radicals in denominators. And we don't leave fractions under radicals. Neither one of these is proper form. We need to make the denominator become rational. How do we do that? The book goes to great lengths to try to explain the process, but let me see if I can put it very simply. We're going to multiply by a fancy name for 1. Something over itself. We're going to multiply by a very clever name for 1 that's going to force that 9 to become a perfect cube. How about this? What if I multiplied the 9 by another 3? Which would cause this to become the cubed root of 27. I'm allowed to do that as long as I also multiply the numerator by the same thing, because after all, cubed root of 3 over cubed root of 3 is just a very fancy name for 1. All I'm doing is multiplying by 1, which doesn't change anything, except the way it looks. It doesn't change what it is. So what's that do for me then? Numerator, I have now the cubed root of 21 over the cubed root of 27, but we should all know very quickly and simply now that the cubed root of 27 is, oh yeah, that's easy, that's 3. Yep, that's 3. We have made the denominator, into a rational number. It's no longer irrational. We've gotten rid of the fraction that used to be under the radical. It's okay to have a radical in the numerator, but it's not okay to have a fraction under the radical. We have settled that issue. This is the simplified version of that. Next example in the book, same concept once again. Square root of 2a over 5b. And allow me to take a little bit of a shortcut this time. I'm not going to go through the step of splitting it. Just imagine in your head that this is square root of 2a over square root of 5b. That part I'm leaving to the head. So, what am I going to do? 5 is not a square. I can't pop out the 5. I certainly can't pop out the square root of a b. I can't have a fraction under the denominator. So I'm going to multiply once again by a very cleverly chosen name for 1. I'm going to multiply by the square root of, wow, if only that 5 were a 5 squared. If only it were a 25. And if only that b were a b squared. Well, you know, I can make that 5 into a 5 squared or a 25. I can make that b into a b squared. How? Multiply by 5b. Numerator, 5b. What happens? My numerator becomes square root of 10ab. Square root of 10ab. Denominator, well, what is the square root of 5 times the square root of 5? That's why we did this. What is the square root of b times the square root of b? Sort of. Oh, we have to take the absolute value, don't we? Yes, even index, we have to take the absolute value. Final answer, square root of 10ab over 5b. Notice what's happened. There is no longer a fraction under the radical sign, and there is no longer even a radical in the denominator. We have rationalized the denominator. Congratulations. We now move on to example 6. Cubed root of a over cubed root of 9x. All right. Well, same story, folks. Same story. We're going to multiply by a very cleverly chosen name for 1. We're going to multiply by a cubed root of something under the cubed root of something. But of course these have to match, otherwise we're not multiplying by 1, and that would not do at all. So these have to be the same. What can I multiply 9 by to make it become a cube? Yes, I could multiply it by another 3. Because think of it this way, by the way. Here's another way to look at it that might, for some of you, be easier. Isn't that 9 just 3 squared? And I wish it was 3. That doesn't look like a square. And I forgot, was that an x? I hope it was. Yes. I just changed the 9 in my head or on my paper. I changed the 9 into a 3 squared, and I wish it were a 3 cubed, because I know the cubed root of 3 cubed. Yeah, the cubed root and the third power cancel. So I just throw in another 3. And here, I wish that were an x cubed. How can I make it into an x cubed? Yeah, I hear what you're thinking. Just multiply by x squared. That'll do it. Same thing up here, of course, 3x squared. So what do I end up with? Numerator, just combine the radicands. Cubed root of 3ax squared. I like to keep them in alphabetical order. I could put the a any place, but I like to have it before the x and after the 3. Down here, what is the cubed root of 3 cubed, or the cubed root of 27? It is 3. And what's the cubed root of x cubed? The cubed root of x cubed is x. Absolute value? No, no absolute value. Not with odd index. We do not use absolute value ever. If you do, it's wrong. We're done. Hey, can we cancel that x with that x? Or can we cancel that 3 with that 3? No. Because that's not really a 3. It's a cubed root of 3. And that's not really an x squared. It's actually a cubed root of x squared. No, you cannot cancel these. Banish the thought. No. And we move on to the next little concept here. I'm going to skip the explanation at the top of 307 and jump right into example 7. I think the explanation they give at the top of 307 is more confusing than necessary. 3 over 2 plus square root of 7. We're going to get that radical out of that denominator. So, oh, I know what we do. I'm not so sure you do. We're going to multiply by square root of 7 over square root of 7. Well, let's see what happens if we do that. Here we have 3 square root of 7. Distributive property, because this is a plus sign. We have 2 square root of 7 plus 7. There, we did it! Oh, wait a minute, we didn't do it. No, we didn't do it. Can we cancel those? That's not a factor. No, we cannot cancel those. So we have failed in our attempt to rationalize the denominator. So what in the world do we do? This is so cool. This is downright fun. All right. We saw in one of the first examples, we saw back in example 3. We know that a plus b times a minus b equals a squared minus b squared. Watch what happens if I multiply this by 2 minus square root of 7. But you can't just do that unless you also... Oh, yes! Yes, we did it here. We also multiply the numerator by 2 minus square root of 7. These have to be the same, so that we're just multiplying by a very fancy name for 1. Makes it legal. So what good is this? Watch what happens. Numerator becomes distributive property. Don't forget your basics. Numerator becomes 6 minus 3 square root of 7. What happens to the denominator? There's a name for these, by the way. These guys are called conjugates of each other. 2 minus square root of 7 is called the conjugate of 2 plus square root of 7. There is something marvelously special about conjugates. When you just change the sign in the middle, they're called conjugates, and here's what happens with conjugates. Use the old a squared minus b squared rule. A squared is 4. What's b squared? Square root of 7 times square root of 7 is 7. Put a minus in between. We get what now? 6 minus 3 square root of 7 over negative 3. We are done. It's over. Oh, not quite. There's one last detail here. I'll tell you, before I get to that one last detail, let's meditate on this for a moment. What is your strategy? In a case like this, if you're trying to get rid of a radical that's attached to something else with a plus or a minus, your strategy is multiply numerator and denominator by the conjugate of the denominator. And what's meant by conjugate? Just change the plus into a minus. Or if this were a minus, you would change it into a plus. Multiply by the conjugate, numerator and denominator. We multiply the numerator and denominator by the conjugate of the denominator. Memorize that phrase. Multiply the numerator and denominator by the conjugate of the denominator. Why? Because every time you ever multiply one of these guys by its conjugate, the radical signs will always, always cancel out. That's what's special about conjugates. When you multiply two conjugates, your answer will always be rational. No more radical. You have rationalized the denominator. Now I say we're not quite done here because there's one last detail. We could factor out a 3 and cancel the 3's. Or we can think of it as simply dividing both of these terms by negative 3. If I divide both of these terms by negative 3, what happens? 6 divided by negative 3. And then negative 3 divided by negative 3 cancels and becomes a positive. And our final answer is negative 2, square root of 7. Checking my answer in the book to make sure I didn't do anything silly. Yep, there it is. Negative 2 plus square root of 7. Let's do another one. I'm not sure I quite get it. Okay, that's why we're going to do another one. 4 plus square root of 2 over square root of 5 minus square root of 2. All right, so what am I going to do? I can't have these radicals in the denominator, so I'm going to very cleverly, because I am indeed clever, and so are you. The rubber chicken may disagree with that, but that's all right. We will multiply both numerator and denominator by the conjugate of the denominator. Yes, denominator. We look not at the numerator, we look at the denominator. I'm going to multiply numerator and denominator by the conjugate of the denominator. That's a lot of words, but it's a simple idea. I'm going to multiply numerator and denominator by the conjugate of the denominator. So I'm going to multiply numerator and denominator by square root of 5, change the sign, that's all there is to it, plus square root of 2. Same thing up here, otherwise I'm not multiplying by 1, and it would therefore not be legal. Get rid of my little box here. Okay. So now what do I have? Well, let's save the numerator for last. That's a little ugly. We've got to apply FOIL up here. There's no shortcut, just FOIL. Well, FOIL is a shortcut, but that's my only shortcut up there. Down here, oh, this is just a case of a minus b times a plus b. We rigged it that way. We very carefully chose this, so we would end up with a minus b times a plus b. So what's the rule? Square this guy. What's square root of 5 squared? 5. Always minus. And then square root of 2 squared is 2. So your denominator is just going to be 3. A squared minus b squared. 3. Numerator, that one's ugly. And the denominator is always easy. The numerator, you have to work a little bit. Firsts, outers, inners, lasts. Firsts, outers, inners, lasts. Yay, rationalization. Yeah. Firsts, 4 square root of 5. Outers, 4 square root of 2. Inners, ooh, what's that? Yeah, that's simple, right? Square root of 10. Lasts, what's square root of 2 and square root of 2? Just plain 2. All over 3, we're done. That's the best we can do. There's nothing to combine here, there's nothing to simplify, there's nothing to factor out. Yeah, we're stuck with this ugly answer. That's the way it goes sometimes. We get an ugly answer, that's okay. Ugly is all right. In math, ugly is sometimes pretty. Hey, that's the end of the section. That was our last example. Let me throw in one more thing here. This comes up. Am I going to assign it? No, I won't assign it, but I'm going to show it to you anyway. Now, forget it. Never mind. I think it'll come up later, so never mind. We're done, except for the assignment. And you know something? I did it again. I didn't put in one single quiz question. Well, I'm not going to cram in both or all 4 quiz questions right here at the end. So that's the way it goes. Next time, maybe I'll remember. But, so forget the quiz. If we go back here for a second. Not this time. Okay. So now, your assignment is as follows. On page 308. Pretty cool that we're in the 300s. Wow, making progress. Numbers 2 through 52 even. Oh no, that's so much! Well, it's a good thing that you have the entire Easter break to work on it. I mean, you could do numbers 2, 4, and 6 on Monday. Spend all day on those first 3 problems. Then you can do 8, 10, and 12 on Tuesday. Spend all day on those 3 problems. I mean, it might take you 6 hours to do those 3 problems. Yeah, spread it out over Easter break. Yeah, you can do 2 through 52 even, no problem. But yeah, speaking of Easter break, wow, I would like to say this is due next Monday, but there is no next Monday. Well, I hope there will be a next Monday. For this Corona thing, you never know. But assuming that all goes well, next week it's our Easter break, so this is actually not due until the Monday after Easter by noon. What day is that? One moment, let me take a look at my calendar. I have no idea. That would be, wow, the 13th. Monday the 13th. I think, did I see that right? Or was I looking at Sunday? Yep, that's right. Monday the 13th. So this is due 4/13 by noon, as are all of my assignments. So by noon on Monday the 13th, the Monday after Easter, don't forget. Yes, you may feel free to get to me early. That's great. I just put it in a folder and I look at it later. So I would encourage you to get it done early, but at least by noon on Monday, a week from this coming Monday. Enjoy your break, and that's all for now. So, farewell, have a marvelous Easter, and please, over the Easter break, take some time to remember what Easter is really all about: the death, burial, and resurrection of our Lord and Savior Jesus. He died for you. He lives for you. Embrace Him and give Him some honor, and think of Him and what He did for us over this Easter break. See you later.